Okay, so the practice problems, I'm just gonna start from the top again. So for the first one, what reaction do you think this is and why? That's like one of the very first ones on the handout.
Itself?
Yes, but yeah, and then what reaction? Like
It's gonna form a heavy acetal.
it forms a hemiacetal, so this would be acetal formation, that's all. So what you have to identify is what reagents you have here and what you think they're going to do to each other. So in this one molecule, we're not given anything else. So from this one molecule, you have to identify that on one side you have an aldehyde, and on another side you have an alcohol. And from this chapter, we know that when you have an aldehyde plus an alcohol, the alcohol just goes around and basically attaches itself to this carbonyl carbon. And then you form either a hemiacetal or an acetal. So since this is the only thing we're given and there's like no extra alcohol in the reagent line, I think this is going to be a hemiacetal formation. So what happens in this reaction is that, this is not the official mechanism, this is like the shortcut, but basically this alcohol swings around and sticks itself onto this carbonyl carbon. And then you have to move one of the double bonds up. So this is a ring formation because it's intramolecular. Yeah, so what you get is I think this is going to be a 5-membered ring. So I'm just going to keep the aldehyde there. Since you're adding something to the aldehyde, the pi bond is kicked up and it's gone. So you have a single bonded alcohol. And then you just count your carbons to make a ring. So 1. But now we identify what functional group we just made. So this is some kind of acetal because you have 1 carbon and 2 oxygen groups attached to it. So do you remember how to identify like which one it is?
So look at the chart where 2 our groups are attached, and you see that's attached to a carbon or an hydrogen. You see it's a ketal or an acetal or heavy acetal.
Yes. Yeah, so step 1, you find the carbon where the 2 oxygens are attached to. So that would be this carbon right here. So now you kind of just ignore the oxygens and you look at which R groups are attached to it. So we have the 2 oxygens, but we also have 1 R group down here, and we have an invisible hydrogen coming out of it to make 4 total bonds. So on that 1 carbon, you have 1 R group and 1 hydrogen. So if that is 1 R and 1 H, it's an acetal. So we know this is either a full acetal or a hemiacetal. And then how do we know if it's hemi or not?
There are. How much there are? What side?
You look at the oxygens.
2 different groups. with the oxygen, then it's hemi, and then it's the same dose.
Yes, so you look at the groups attached to the oxygen. You can either have an R attached to the oxygen, like this case, like you have an oxygen and you have more carbons attached to it on the side. Or looking at this oxygen, you just have an alcohol with a hydrogen attached to it. So if you have two OR groups attached to this one carbon, it's going to be a full acetal. If you have one OR and one OH, it becomes a hemiacetal. Okay. So for the second one, we already did it, but can someone explain to me what happened here? Yes, so we formed a hydrate. All you need to recognize when you have an aldehyde or ketone and you give it just water, it's usually like H3O over H2O. You just add, well, you just turn this carbonyl into two alcohols. So this is called a geminaldiol or a hydrate. Okay, so the third one, what's happening?
Are we gonna form the cyclic oxygen thing?
Yes, we are. And how do you know that?
When over to the side.
Exactly. So whenever you see an aldehyde or ketone and a diol like this, you know it's going to be cyclic acetal formation. It's usually this specific diol. So you know when you have an alcohol and aldehyde, you just add that alcohol to the carbonyl carbon. But now you have two alcohols that are attached to each other. So they kind of take turns and both add themselves to the same carbon. But they are attached like as a free molecule, so they stay attached after you've added them to the carbonyl. So the shortcut way, when you see something like this, you just draw it, but then you are going to replace the carbonyl. So now we just attack either of these two oxygens. We just like glue them onto this carbonyl carbon right here. So we have two new bonds to two oxygens. And then this R group that's connecting them stays present in the final molecule. So you have like a bridge kind of cyclic looking thing. And then what kind of acetal is this besides cyclic?
It's the full one.
It's just the full acetal. So now in the reaction right below that one, you have this molecule which has a ketone and an ester on it. And then what is this reagent over here? It's the exact same thing. So it's just this diol we had above, but we're now in condensed formula. So what happens?
Attack carbon. Doesn't attack carbon. Right?
On the left.
Yeah.
So this chapter is all about aldehydes and ketones. So the other carbonyl here is an ester. Esters are not reactive enough. to participate in the reactions of this chapter. So we're only concerned with aldehydes and ketones. So we're only really looking at this one. And then we do what we did up here to this ketone. So we turn it into that cyclic looking acetal. And the ester is just unaffected. Okay, and now we have lithium aluminum hydride. So what does that do? It makes alcohol. So lithium LAH is a strong enough reducing agent to turn esters into alcohols. And you will need to know most of the reagents from chapters 11, 12, and 15 for this exam. Because there's a lot of multi-step problems like this. Not a lot, like a decent handful. And we'll give you a bunch of reagents and ask you for some random intermediates. And there's a decent amount from 11, 12, and 15. So LAH is going to turn this ester into what kind of alcohol?
Primary.
Primary. Because you have that leaving group. That's it. That's your final product.
The way we get rid of that, the diol, the acetyl, is we just add acid.
Mhm.
And then it makes it just back into ketone.
Yeah. Okay, so the reaction right below it. Which reaction is it? So how do you know it's formation of an imine?
So primary.
Yes, it's a primary amine. So you have an NH2 attached to one R group, so this is a primary amine. We know that if you take an aldehyde or a ketone and mix it with a primary amine, we get an imine as the final product. So what's the shortcut for doing this reaction?
Place the O with it and
So all we have to do, we look at this imine, we chop off the H2. And then the rest of the amine, we can just replace the oxygen on the carbonyl with that. So we're gonna chop off the O, we're gonna chop off the H2, and then just put the NPH right where the O was, and then that's your imine.
Is there any ring expansion?
No, because there's no carbocation going on. Okay, and then the one below it, what's the reaction called? It would be hydrazone formation if we didn't have the KOH present. Yeah, it's Wolff-Kishner reduction. So when you have a hydrazine and KOH, and I think water probably, and heat, is a Wolff-Kishner reduction. So in that reduction, all you need is a ketone and these reagents, and then you just cut off the ketone and it becomes a CH2. So So the final product of this, we're just getting rid of this whole thing. Then what's another way to reduce ketones like this? To reduce them into CH2s. Condensate.
What?
The condensate reduction. It does the same thing as this. Yeah, so with Wolff-Kishner, it first goes through an amine intermediate, and then the base and the water kind of like gets rid of the amine. Okay, so the last one on this page, what's the reaction? Yeah, oxide formation, and it's the exact same deal. Cut off the H2, cut off the oxygen, put the amine group where the oxygen was. And then the final functional group is called an oxide. And then this reagent is called a hydroxylamine.
What's this reaction called?
Just oxide formation.
Before that.
Wolff-Kishner reduction. Let's start with the last one, right?
Yeah.
So now we have a ketone, and then what is this group called?
Hydrazine.
Yeah, hydrazine. So ketone plus hydrazine gives you what?
So
So exact same thing happens. Get rid of the H2, get rid of the oxygen, put the amine where the oxygen was. And this is called a hydrazone. Okay, now this reaction, what are we doing here? It is Wittig, and how do you know that? So every time you see this PPH3, you can identify it as either an ylid or like an ylid precursor. You know, it has something to do with Wittigs. So what do you know? Like, what do you know to do when you see a Wittig reaction?
That's the with the carbon at the top spot. Positive. And then like the positive phosphorus reaction.
That's how you get that square. So what you need to do, like a full Wittig mechanism to actually like join the two R groups together, you need to kind of like do that square arrangement transition state. But before that, you need to make sure that you actually have a functional ILID. So if you just have like a PPH3 floating around, like it's not going to do anything. And I think on the exam, there are a couple of questions where you had to like form the ILID first. Just make sure you have like the full ILID before doing the reaction. So on the test, you'd see something like the ILID, and then you'd have to pick an alkyl halide, or it would give you the ILID and the triphenyl phosphate and an alkyl halide, and then you'd have to figure out the right Wittig, and then find out the final product from that. So yeah, in this case, we have everything, so we can just go ahead and draw that transition state. So we're going to line up the oxygen with the phosphorus. Like this, because the oxygen is nucleophilic and the phosphorus is electrophilic. And then the carbon anion, we're going to line that up with the carbon of the carbonyl. So the carbon anion is delta negative, which makes it nucleophilic. And the carbon from the carbonyl is delta positive, so electrophilic. Now we can draw our arrows. So the nucleophile is going to go ahead and attack each electrophile. So the carbon attacks the electrophilic carbon, and then the oxygen is just going to go ahead and attack the electrophilic phosphorus. Once those attacks happen, it's going to unfold into something like this. So once you've established this as your transition state, you can kind of see clearly what the products are going to be. So I just split it down the middle at this point, and I know that at the top is like the R groups of interest. That's what we want our final products to be. We want to merge those together. And on the bottom is like the side product that's just whatever. But we know that we're going to split it down the middle, and then each of these groups, like on the left and the right, they're just going to be joined together by a double bond. That happens when these arrows attack like this. So the carbon phosphate bond breaks and then makes a double bond here. And then the oxygen carbon bond breaks and makes a double bond there. So they're just unfolding into two separate alkene products. So the top half, the products that we are concerned with, is going to look like this. We just took those two R groups from the transition state, put an alkene in between them, and then that's the final alkane product of this Wittig. So I like doing it that way if I get a little confused, because if you just draw it out, then there's like no way you're really gonna get it wrong. But the shortcut method, which is also pretty easy, you're gonna arrange your ILID and ketones like in this kind of formation. So I like putting them horizontal to each other, so the ketone is like facing this way. And then the illid, the R group is also just like facing each other. So now we know that this stuff, the bottom side product that we're not concerned with, we're just gonna go ahead and cut that off. So I'm gonna cut this down the middle, and I know I'm gonna get rid of this oxygen. And I'm also going to cut this, and I'm also gonna get rid of the triphenyl phosphate. Yeah, so now all that's left is that you take these two R groups and glue them together. So I just add this R group onto this alkane. So just replace the oxygen with the R group that's attached to the triphenyl phosphate. So we know that we had a ketone, but we got rid of the oxygen and replaced it with a CH2. That's your final lytic product. Was that it? Yeah. I mean, sometimes they write it, sometimes they don't. Okay. So we're good with lytics. This reaction over here, you guys remember it? It is Toland's test. What does Toland's test do?
Just change the aldehyde into a.
Yeah. So Toland's test alone, I think that would just be the silver nitrate thing. So if you have just an aldehyde, okay, I don't really have one. So if we got rid of the H2O and we just had that silver thing with the aldehyde is going to turn into something called a carboxylate ion. So basically a deprotonated carboxylic acid. But we do have the water on the bottom. So because that's there, this carboxylate is going to get protonated and we just turn the aldehyde into the carboxylic acid. So the bottom one, I don't think was ever covered, and I'm not even sure why I added it. But basically, if you have a ketone and an NH3, you just turn it into an imine. So, but there's no R groups attached to it, so just replacing the oxygen with an NH group. I'm really confused why that's there, but now you know. Yeah, I would say this is still an imine because I think the H counts as an R group. And then the imine is just if you have this functional group. All right, so it's retrosynthesis time. So I asked for this final product. I did not give a starting product. I think I should. Yeah. So with a few steps, we're going from this molecule into that final product. hydration. Oh,
Hydration.
hydration is not a part of it.
With like.
Yes.
Or
So, okay, no, actually, no, there's no ALH4. We're adding something, we're trying to turn this ester into this thing over here. So what do you think we use to achieve that?
Looks like acetal.
It's not an acetal formation because there's only one oxygen group. But it's the same principle, adding stuff to carbonyl. Huh?
A diol.
No, because at a diol, we also have 2 oxygens in the final product. No, if it was Wittix, we have an alkane somewhere. The only alkane is in this ketone.
Is it like oxidation?
I don't think there's any oxidation here. But I did tell you he was gonna pull reagents from chapters 11, 12, and 15.
Oh, so do you
Yeah.
have to use SOCO2 to make it a?
No.
Oh my God.
Yeah, SOCl2, maybe if it was a carboxylic acid.
Won't react with the ester.
Huh?
It won't react with the ester.
What would it?
SOCO2.
Yeah, so no, it wouldn't. Or maybe it would. It would be a Grignard. So we know at one point during this multi-step synthesis, we're doing a Grignard because we're adding this R group to what used to be a carbonyl. So a Grignard happens somewhere in this reaction. Could we go directly from this to this with a one-step Grignard reaction? Why not?
Just hang it up.
The Grignard?
Yeah.
No, if it was just a pentagon, there would be an extra carbon-carbon bond over here. But why couldn't we go from that to that in one step? Because the ester, and then there's also a ketone. Yes, you have to protect the ketone. What's one way that we learned in chapter 16 that you can do that?
Diol.
Yeah, you use a diol. Well, yeah, use a diol. You basically use a cyclic acetal. So one big application of cyclic acetals is that they're used as protecting groups. So in this case, you have to recognize that you were doing a Grignard at some point in the reaction. You couldn't do a Grignard to this molecule straight up because there's 2 carbonyls that the Grignard could have added to. So we could have had some like weird side product that we didn't want. So we're gonna have to protect this ketone since it remains unchanged with a cyclic acetal. And then we're gonna do whatever we want to the ester. So what order? Huh?
The protective group first.
Yes, and what do we use in the protecting group reagents?
Cyclic acid. Wait. Well, cyclic acetylation.
Yes, you use a diol with an acid. Okay, so then that gives you your cyclic acetal. It doesn't affect the ester because the ester is too reactive. So what now? We've protected the ketone. What do we do now?
Add the Grignard.
Yes. So what Grignard reagent do you think we're going to use? For final product, you have one ring that's directly attached to the carbonyl carbon. It's not like this kind of ring where it's separated. So what kind of Grignard did we have to use?
They couldn't get tested with it.
Hmm?
The Grignard couldn't be tested.
Okay, so it's not a ring like in its Grignard reactant form, but as you're doing the reaction, like when you add it to the carbonyl, then it becomes a ring. So what would that require?
So the Grignard have like could have two pieces on it, two
Yeah. So. So we added 4 carbons as a ring onto the carbonyl. So just like you said, you're gonna have that 4 carbon chain with an NGBR on each side. I'm gonna take a detour. So because you have an NGBR on each side, you can just, cross it off and put an anion on each side. And then we remember from Grignard's that basically the anion just goes ahead and attaches itself to the carbonyl. But since there's 2 very reactive anions in this one carbon chain, it's going to do that twice. So both sides are going to come back and attack the ester. And this is possible because you have this OR that's part of the ester, which is a leaving group. So you could go ahead and add twice. So now we get that ring thing that we wanted. We get the alcohol with the pentagon attached right on it. But we still have this cyclic acetal to deal with. So how do we turn it back into the ketone for the final step? Yeah, we just add acid. So what do we think? You have something probably easier than that, mostly because it's multiple choice, but just like know the rest of the stuff. We just added acid to the acetal and it turns back to the ketone. Well, it's actually a ketone. Yeah, so to go from aldehyde or ketone to acetal or ketal, add alcohol. To go back, add acid. Okay, so the very last reaction, it's intermolecular again, because we are only given this one reagent, but what do you think happens? And what reaction is this?
the enemy formation,
And how do you know that?
the secondary.
Exactly. So if we have a carbonyl plus primary amine, we get imine. If we have a carbonyl plus secondary amine, those 2 R groups, you turn it into an enamine. So it's the same idea. You basically just cut off the oxygen and put this amine group where the oxygen was. We're just gonna swing that over and attach it there. Okay, but there's one important thing for enamine formation. So with an imine, we thought the double bond was part of the nitrogen carbon bond. In this case, we still have to do a double bond, but it's not going to be directly attached to the nitrogen. It's going to be on one of these side carbons or coming from one of those side carbons. So with an enamine, like once you get the space structure, then you have to determine which side of the carbonyl or like the original carbonyl the double bond is going to go onto. So we know we put the NH over here where the oxygen used to be. But yeah, now which side would we put the double bond on to make it more stable? The left or right? The left.
Oh, you got the beginning one?
No, it's just this like beginning thing translates to this. Yeah, so it would be the right side, right? Yeah, so basically with an enamine formation, like once you've attached the nitrogen wherever you want to attach it, we do an elimination reaction from one of these side hydrogens. And you're going to do the elimination reaction from the more substituted side. In this case, that would be the right side. So you would put the double bond there. Okay, I feel like that was really confusing because I didn't use the mechanism. Like I just look at this, I identify it's an enamine formation, and I know that like the structure of an enamine is this. So you have the secondary amine, and then we have like what the carbonyl or like the original aldehyde or ketone. So once we've replaced it, once we replace the oxygen on top with the secondary amine, I know that there's going to be a double bond, one carbon bond away from the amine, because that's just what an enamine functional group looks like. So now there's going to be a double bond either here or here, because that's what an enamine is. So when you're doing enamine formation, you have to pick which side to put the double bond on, and you pick the more substituted side because it's more stable. But since you need it to be an elimination reaction, you can't have like a quaternary carbon. So you have to make sure there is a hydrogen present on that side where you could have done an elimination reaction. If this looked like this, you'd have to put a double bond on this side.
So what's the reason why you decided to put it inside the ring instead of on the left side?
Yeah, because it's tertiary. So it's more substituted.
Yeah, for this case?
Yeah.
Yes, you put it here because it's tertiary. And then there's also an alpha hydrogen that we can do an elimination from.
Why would we put it on the right side where the tertiary group is?
Why wouldn't you put it here?
Yeah.
Because to get the double bond there, we need to do an elimination, which requires a free hydrogen. Because quaternary, there's no free hydrogen. So that's the only exception for the stability thing. Was that still confusing or does that make sense? Okay. So that's the handout. We finished it. I can stay and do something from the homework if someone wants to.